This is an audio recording for visually impaired students from the book Pardeep's Inorganic Chemistry, Volume 1 by Dr. K.K. Bhasin. Chapter 1 Atomic Structure. One of the earliest models of atom was proposed by Rutherford. According to Rutherford's model, most of the mass of an atom is concentrated in a small dense nucleus. The electrons are revolving around the nucleus and occupying most of the volume of the atom. The nucleus of hydrogen atom is a proton. The nuclei of all other atoms are composed of protons and neutrons. To explain why the negatively charged electrons do not fall into the positively charged nucleus, Niels Bohr, 1913, proposed that the energies of electrons in atoms are quantized, that is, they can have only certain fixed values. Thus, Bohr pictured the electrons as circling around the nucleus in orbits. Bohr's model of an atom was successful in explaining the atomic spectrum of hydrogen atom. However, it failed to explain the spectra of multi-electron atoms. Bohr's model of atom also failed to explain the splitting of special lines in a magnetic field, a phenomena called Zeeman effect, as well as in electric field, a phenomena called Stark effect. The serious objection to Bohr's model of atom came from the new revolutionary ideas of Debrock and Hinsberg, who introduced the concept of wave character of electron in addition to the particle character of electron, and pointed out that it is impossible to measure both the position and velocity of submicroscopic particles like electrons at the same time. Within a short time, a radically different model called the quantum mechanical model was proposed to account for new observations. In fact, the sophisticated quantum mechanical model of atomic structure was derived from the work of Louis de Broglie. First heading 1.1 De Broglie idea of matter waves. In case of light, some phenomena like interference, diffraction, reflection, refraction, etc. can be easily explained by assuming light to have wave-like character. However, there are certain other phenomena like black body radiation and photoelectric effect that can only be explained by assuming light to have particle-like character. Thus, light is said to possess dual character of a wave as well as of a particle. This bold statement of dual character was stated by Einstein in 1905. The credit for the discovery of an electron in the discharge tube experiment majorly goes to Sir J. J. Thomson. Various experiments performed on these rays conclusively proved the particle nature of electron. In later experiments, the mass of electron was determined to be 9.1 into 10 raised to power minus 31 kg. Even in Bohr's model of atom, the electron is treated as a particle. It was only in 1924 Louis de Broglie, a French physicist, suggested that electron can also possess a dual character of wave and particle, just as in case of light. This laid the foundation of a new subject called wave mechanics or wave nature of matter. In other words, wave associated with a matter is called a matter wave. Thus, according to de Broglie, all material particles in motion possess wave characteristics. De Broglie showed that just as electromagnetic waves could be treated as streams of particles, photons, moving particles could also exhibit wave-like properties. Thus, it is important to picture electrons either as particles or as waves. Before we take up the details of this chapter, it is appropriate to know an interesting aspects of the wave-particle journey. Sir J. J. Thomson got the Nobel Prize by proving electron as a particle. His son, G. P. Thomson, received the Nobel Prize for proving electrons as a wave. It is indeed very interesting and exciting. According to de Broglie, the wavelength lambda associated with a particle of mass m moving with velocity v is given by the relation lambda is equal to h upon mv, where h is equal to Planck's constant, mv is equal to momentum of the particle. The waves associated with the material particles are called the matter waves. The equation 1.1 is known as the de Broglie equation. Derivation of de Broglie relationship. By combining the mass-energy relationship proposed by Max Planck and Albert Einstein, the de Broglie relationship can be derived. According to Planck, a photon of light having energy E is associated with the wave of frequency nu as E is equal to h nu. And according to Einstein, mass and energy are related as E is equal to mc square, where c is the velocity of light. Equating the equations 1.2 and 1.3, we get h mu is equal to mc square. Since nu lambda is equal to c, or nu is equal to c upon lambda, hc lambda is equal to mc square, h upon lambda is equal to mc, it implies that lambda is equal to h upon mc. This equation is valid for a photon. Debrock suggested that on substituting the mass of a particle m and its velocity v in place of velocity of the light c, the equation can also be used in case of the material particles. Thus, the wavelength of the material particles is lambda is equal to h upon mv. This equation is known as the Debrock equation, or in other words, lambda is equal to Planck's constant upon momentum. Since h is constant, lambda is directly proportional to 1 upon momentum, or lambda is inversely proportional to momentum. It means that the wavelength is inversely proportional to the momentum of the particle. Significance of de Broglie relationship. Although the dual nature of matter is applicable to all material objects, but it is significant for the microscopic bodies only. For large bodies, the wavelength of the associated waves are very small and cannot be measured. Therefore, practically all the large bodies are said to have no wavelength. Thus, any material body can have the wavelength, but it is measurable or significant only for microscopic bodies such as electrons, protons, atoms, or the molecules. Experimental verification of wave character of electrons. The wave character of electron was experimentally verified by Davison and Germer in 1927 and G.P. Thomson in 1928 by observing diffraction pattern consisting of concentric rings using a crystal. Davison and Germer subjected a beam of electrons emitted from a tungsten filament to fall on the surface of a nickel crystal and observed the scattered rays as concentric dark and bright rings on the photographic plate in the figure. These rings are called the diffraction rings, and the associated phenomena is called diffraction. The diffraction pattern of electrons by crystals was similar to the produced by X-rays. Since the wave character of X-rays is well established, therefore, electron must possess a similar wave character. Moreover, the wavelength of electron determined from the diffraction studies were found to be the same as calculated from de Broglie equation. Thus, the simple experiment gave a direct evidence for the wave nature of electron. Similar findings were observed when G.P. Thomson performed the experiments using a thin foil of gold instead of nickel crystal. It is important to add the diffraction patterns can also be observed with other microscopic particles like proton, neutron, hydrogen atom, etc. De Broglie equation and angular momentum. De Broglie equation can explain successfully the Bohr's postulate regarding the angular momentum of the electron. If you recall, Bohr's model postulated that the angular momentum of an electron moving in a particular orbit is quantized, that is, it has definite values which are integral multiples of h upon 2 pi. However, according to the Broglie concept, electron is not only a particle but also possess the wave character. Thus, in order that the wave may completely be in phase, the circumference of the orbit must be an integral multiple of wavelength lambda. That is, 2 pi r is equal to n lambda, or lambda is equal to 2 pi r upon n, where r is the radius of the orbit and n is an integer. However, according to de Broglie equation, lambda is equal to h upon mv, so 2 pi r upon n is equal to h upon m nu, or 2 pi r is equal to n into h upon m nu. On rearranging, we get mvr is equal to n into h upon 2 pi. It means that the angular momentum of an electron is an integral multiple of h upon 2 pi. This is basically what Bohr postulated in his model of atom. Distinction between matter waves and electromagnetic waves. Matter waves differ from electromagnetic waves in various aspects and are given below. First, electromagnetic waves. Electromagnetic waves are associated with electric and magnetic fields which are perpendicular to each other and to the direction of propagation of the rotation. Matter waves. Matter waves are not associated with electric and magnetic field. Second, electromagnetic waves. Electromagnetic waves do not require any medium for propagation. It means that these can pass through vacuum. Matter waves. Matter waves do require a medium for propagation. It means that these cannot pass through vacuum. Third, electromagnetic waves. Electromagnetic waves travel with the speed of light 3 into 10 raised to power 10 centimeter per second. Matter waves. Matter waves generally travel with the speed less than that of light. Fourth, electromagnetic waves. The wavelengths of electromagnetic waves are governed by the relation lambda is equal to c upon b, where v is the nu is the frequency. Matter waves. The wavelength of matter waves are governed by de Broglie relation lambda is equal to h upon mv, where v is the velocity. Fifth, electromagnetic waves. Electromagnetic waves leave the source. Matter waves. Matter waves do not leave the moving object. Now there are some examples based on de Broglie wavelength. Next heading 1.2 Hinsberg's uncertainty principle. In 1927, Werner Hinsberg pointed out that one cannot measure accurately both the position and velocity momentum of a microscopic particle. On the basis of this observation, Hinsberg put forward a principle known as Hinsberg's uncertainty principle. According to this principle, it is not possible to determine precisely both the position and the momentum velocity of small moving particles with accuracy. Consider a photon of light incident on a particle. If the particle is of reasonable size, its position or the velocity will not be altered by the impact of light photon. But it is not so when the particle is extremely minute, such as an electron. It will suffer a change in the velocity as well as in path due to the impact of even a single photon. The path and velocity of an electron after the impact of photon may be quite different from the original path and velocity. In view of Hinsberg's uncertainty principle, the Bohr's model, in which electron is considered as particle moving in the definite orbit, that is well-defined path, does not hold good. It is thus more accurate to say that electron is associated with definite energy than to say that it belongs to a particular orbit. Mathematical expression for the uncertainty principle is delta x into delta p is less than equal to h upon 4 pi, where delta x is uncertainty in position and delta p is uncertainty in momentum. The sign less than or equal to means that the uncertainty can never be less than h upon 4 pi. The constancy of the product of uncertainty means that first, if delta x is small, that is the position of particle is measured accurately, then delta p would be large and thus the uncertainty in momentum will be large. Second, on the other hand, if delta p is small, the momentum of the particle can be measured accurately and the uncertainty in the position, that is delta x, will be large. In brief, it is impossible to determine simultaneously the position and momentum of a microscopic particle with absolute accuracy or certainty. Werner Hinsberg, the German physicist, won the Physics Nobel Prize in 1932 for these contributions. Explanation of uncertainty principle. To explain the uncertainty principle, let us consider an object moving in a circular path. In order to determine the position of an object, we should shine light on the object. When a beam of light falls on the object, the photons of the incident light strike the object and the reflected photons are seen by our eyes. If the object is massive, that is large, its position and velocity will not change by the impact of the striking photons. As a result, one can measure the position and velocity of the object simultaneously. However, in case of microscopic objects such as electrons, photons, neutrons, etc., the striking photon of light will disturb the position as well as the velocity of the particle from its normal path. Due to change of path of electron, its velocity also changes and thus the determination of its exact velocity becomes impossible. Although the position of the electron has been pointed in the microscope, figure 1.3 clearly demonstrates how the position of the electron changes by the impact of photon. Thus, it is impossible to determine simultaneously the exact position and momentum of the microscopic object. According to the principle of optics, the accuracy with which the position of a particle can be measured depends upon the wavelength of light used. The uncertainty in position is plus minus lambda. It implies that the shorter the wavelength, the greater is the accuracy. But one should realize that shorter wavelength means higher frequency and hence higher energy. The energy photon on striking the electron changes both the speed as well as the direction. On the other hand, if we use light of longer wavelength, the velocity of or momentum of the striking particle will not change appreciably, but it will not be able to measure the position of the particle accurately. This will increase uncertainty in the determination of position. Thus, we cannot determine the position and momentum of moving microscopic particles simultaneously with certainty. The uncertainty principle does not bother us at all in our daily routine life. This is because we come across only large objects which we can see with our eyes without altering their motion. The position and velocity of macroscopic massive objects can be determined accurately. Now there are some examples based on Hinsberg's uncertainty principle. Next heading 1.3 Spondyger wave equation. Erwin Spondyger 1926 proposed a simple idea that if the electron behaves like a wave, it should obey the classical equation of wave motion. On substituting Debrock wavelength given by the relation lambda is equal to h upon mv into the classical wave equation, Spondyger obtained an equation that describes the 3D wave motion of the electron. This equation, popularly known as Spondyger wave equation, can be written in its simplest form as curl square psi upon curl x square plus curl square psi upon curl y square plus curl square psi upon curl z square plus 8 pi square m upon h square into e minus v into psi is equal to 0, where x, y, z are the space coordinates. M is the mass of the electron, E is the total energy, V is the potential energy, H is the Planck's constant. Psi is a great letter spelled as psi, is the amplitude of the electron wave and is called wave function. It is important to note that the wave function psi is dependent upon the variables x, y and z and is expressed as psi x, y, z. For convenience sake, it is simply written as psi only. Curl square psi upon curl x square represent the second derivative of psi with respect to x. Curl square psi upon curl y square represent the second derivative of psi with respect to y. And curl square psi upon curl z square represents the second derivative of psi with respect to z. Derivation of Schrödinger wave equation. Schrödinger considered that the nucleus of an atom is surrounded by a vibrating electron wave that can be compared with a stationary or standing wave formed by a vibrating string fixed between 2 points as shown in figure. The general equation for such wave motion in one direction is given by sign equation as psi is equal to a sine 2 pi x upon lambda, where a is a constant, lambda is the wavelength and psi is the amplitude of the wave at a distance x from the origin along the space coordinate in one direction. On double differentiating equation 1.7 with respect to x, we get d psi upon dx is equal to a dot 2 pi upon lambda cos 2 pi x upon lambda, because d upon dx sin x is equal to cos x. D square psi upon dx square is equal to a dot 2 pi upon lambda dot 2 pi upon lambda minus sin 2 pi x upon lambda is equal to minus 4 pi square upon lambda square a dot sin 2 pi x upon lambda, because d upon dx cos x is equal to minus sin x. Substituting the value of a sine 2 pi x upon lambda is equal to psi from equation 1.7 into equation 1.8, we get d square psi upon dx square is equal to minus 4 pi square upon lambda square psi, or d square psi upon dx square plus 4 pi square upon lambda square psi is equal to 0. Now, according to Debrock relation, the wavelength is given by lambda is equal to h upon mv. Substituting the value of lambda in equation 1.9, we get d square psi upon dx square is equal to 4 pi square m square v square upon h square psi is equal to 0. Now, considering the electron as a particle, the total energy A of the system is defined as the sum of the kinetic and potential energies as E total is equal to E kinetic plus E potential. Thus, E total is equal to half mv square plus v, or mv square is equal to 2 into E minus v, or v square is equal to 2 into E minus v upon m. Substituting the values of v square from equation 1.11 into equation 1.10, we get d square psi upon dx square plus 4 pi square m square upon h square dot 2 e minus v upon m psi is equal to 0, or d square psi upon dx square plus 8 pi square m upon h square e minus v psi is equal to 0. The equation 1.12 is the Schrödinger wave equation for the wave motion in x direction only. Similarly, the Schrödinger wave equation in y and z directions may be written as d square psi upon dy square plus 8 pi square m upon h square into e minus v into psi is equal to 0, and d square psi upon dz square plus 8 pi square m upon h square into e minus v into psi is equal to 0. The Schrödinger wave equation for wave motion of electron in x, y and z directions may be written as curl square psi upon curl x square plus curl square psi upon curl y square plus curl square psi upon curl z square plus 8 pi square m upon h square into e minus v into psi is equal to 0. The above equation is usually written as del square psi plus 8 pi square m upon h square into e minus v into psi is equal to 0, where del square spelled as del squared is a mathematical operator called as Laplacian operator. The potential energy V in the Schrödinger wave equation in 1.15 can be easily calculated when we take into consideration the energy of the electron. The potential energy of the electron when at rest and at infinite distance from the nucleus is generally taken as 0. The potential energy acquires a value when the electron is brought at a distance r from the nucleus and is given by the equation V is equal to minus positive Ze into E upon r is equal to minus Ze square upon r, where plus Ze is the charge on the nucleus, Z is equal to atomic structure and E is equal to charge on the electron. Consequently, the equation 1.15 for one electron atomic system in 3-dimensional may be written as curl square psi upon curl x square plus curl square psi upon curl y square plus curl square psi upon curl z square plus 8 pi square m upon h square into E plus Ze square upon r into psi is equal to 0. Solutions of Schrödinger wave equation. Like other differential equations, the Schrödinger wave equation has many solutions, values of psi. However, all the solutions do not have the physical significance and thus are not acceptable. The first requirement in applying the Schrödinger equation to a particular system is to obtain a suitable expression for psi, showing how the wave amplitude varies from distance along the x, y and z axis, and then to derive the solutions of the differential equation, only those wave functions which satisfy certain conditions and which have the physical significance are acceptable. These are called the eigen functions of the system. The corresponding energy to the eigen functions is called the eigenvalue. Conditions which a wave function psi must satisfy before it is acceptable are First, psi must be single valued. It must have a single value at any point in space. Second, psi must have a finite value. Third, psi must be continuous. Fourth, psi must be normalized. That is, the probability of finding the electron taken over all the space must be unity. That is 1. Fifth, psi must be 0 at infinity. Therefore, it can be summarized that the wave functions of Schrödinger wave equation must be single, valued, finite, continuous, and normalized. Eigenfunction. Eigenfunctions are the solutions of Schrödinger wave equation which have physical significance and correspond to certain definite energy values. These wave functions represent the orbitals. Eigenvalues. These are the definite values of total energy for the solution of Schrödinger wave equation that have physical significance. Applications of Schrödinger wave equation to hydrogen atom. Schrödinger wave equation has been successfully applied to simple systems like hydrogen atom. In case of the hydrogen atom, Z is equal to 1 and thus V is equal to minus E square upon R. Accordingly, the Schrödinger wave equation can be written as curl square psi upon curl x square plus curl square psi upon curl y square plus curl square psi upon curl z square plus 8 pi square m upon h square into E minus E plus E square upon R into psi is equal to 0. This is the time independent wave equation and describes the behavior of the electron in the hydrogen atom. The equation was arrived not by any mathematical treatment but just by mathematical intuition. The above treatment thus is no way is a proof of Schrödinger wave equation. In fact, the Schrödinger wave equation is not derivable, but it just shows that the equation results from the assumptions. First, that the behavior of an electron in an atom is analogous to a system of standing wave. Second, that de Broglie relationship lambda is equal to h upon mv describes the wavelength of an electron. Justification of the above equation 1.18 for the hydrogen atom is found in the fact that the solution of the equation gives the value of the energy which agrees well with those obtained experimentally from atomic spectra or calculated from the equation given by Bohr for his model of atom. E star is equal to minus 2 pi square m e power 4 z e square upon n square h square, or E is equal to minus r into z square upon n square, where r is equal to 2 pi square m e power 4 upon h square. R is the constant known as Rydberg constant. For hydrogen atom, z is equal to 1. The lowest energy state corresponding to n is equal to 1 equals to r, which has a value 1312 kilojoule per mole. Thus, Schrödinger wave approach leads to exactly the same allowed energy as those previously calculated from the Bohr model. In addition, the most probable radius for the 1s electron in hydrogen atom from wave mechanics is also the same as determined earlier by Bohr radius 0.529 Armstrong from equation 1.24 Bohr model. R is equal to n square h square upon 4 pi square m e square z square. R is equal to a naught into n square upon z square, where a naught is equal to h square upon 4 pi square m e square. A naught is called the Bohr radius. For hydrogen, z is equal to 1. Allowed values of r is equal to r 1 a naught, 4 a naught, 9 a naught, for n is equal to 1, 2, 3 respectively. Next heading 1.4 Significance of wave function psi. Schrödinger wave equation is a second order partial differential equation. The symbol psi in the equation is commonly termed as the wave function, and it represents the amplitude of the electron wave. You have come across different kinds of waves such as water waves, sound waves, or electromagnetic waves. In case of water waves, it is easy to understand the amplitude of the wave. The amplitude of water wave is given by the distance water moves up or down the mean water level, but there is no direct way of measuring the amplitude in case of sound and electromagnetic waves. In case of light waves, the square of the amplitude of the wave at a point is proportional to the intensity of light. Intensity of light is directly proportional to amplitude square. It means that the intensity of light is proportional to the density of photons at that point in space. If we apply the same concept to electron wave function, the square of the amplitude of electron wave psi square should mean the intensity of finding electrons at that point. According to uncertainty principle, the position of electron subatomic particle cannot be determined with certainty. It means psi square determines the probability density and not the density of finding the electrons at that point. This means that when psi square is high, electron density is high, that is, the probability of finding the electron is high. If psi square is low, electron density is low and the probability of finding the electron is low. Something more about psi. We have learned the solutions of Schrödinger wave equation give psi values that can be either positive, negative, or imaginary value, but psi square is always real and has a positive values. Substituting the values of m, e, and h, we get is equal to minus 2.17 into 10 raised to power minus 18 upon n square joule per atom is equal to minus 1311.8 upon n square kilojoule per mole, or is equal to 1312 upon n square kilojoule per mole. If psi square is positive or negative, psi square is always positive. This is because the square of a negative value is always positive. Sometimes a new quantity psi star is used instead of psi square. This is used in the case of wave function psi is imaginary. An imaginary wave function can be expressed as psi is equal to a plus iota b, where a and b are the real number and iota stands for iota is equal to root minus 1. Psi star, read as psi star, is a complex conjugate of psi and is expressed as psi star is equal to a minus iota b. Now psi into psi star is equal to a minus iota b into a minus iota b is equal to a square minus iota square b square is equal to a square plus b square, because iota square is equal to root over minus 1 square, which is equal to minus 1. Thus psi into psi square becomes a real quantity. However, if psi is real, then psi is equal to psi star. It means psi into psi star is equal to psi square. Normal and orthogonal wave functions. We have learned in the earlier section that psi represents the amplitude of the electron wave, whereas psi square determines the probability density of finding the electron at a point. If we sum up all the probabilities of finding the electron over the whole space, it must be unity. A wave function that satisfies the above condition is said to be normalized. Mathematically, it is expressed either as integration of minus infinity to plus infinity psi square dot dx dot dy dot dz is equal to 1, or integration of minus infinity to plus infinity psi into psi star dx dy dz is equal to 1 if psi is imaginary and not real. It means that we integrate psi square or psi star with respect to the volume element represented by the product of dx dy and dz from minus infinity to plus infinity, that is over the whole space around the nucleus. It should come out to be unity. This condition of normalization is reasonable in view of the fact that the probability must become certainty somewhere in the universe. However, we have learned that psi square or psi star is proportional but not equal to the probability of finding the electrons is given by volume element dz dy dz. In such case, the wave function can be normalized by multiplying by a constant n so as to give a wave function which is equal to the probability in a given volume and element. The product of the constant n and the wave function is called the normalization constant. Mathematically, it can be represented as integrate minus infinity to plus infinity n psi into n psi dx dy dz is equal to 1, or n square integration minus infinity to plus infinity psi square dx dy dz is equal to 1, or integrate minus infinity to plus infinity psi square dx dy dz is equal to 1 upon n square is equal to n power minus 2. The normalization constant n can be evaluated from the above expression. In case of psi is imaginary, psi star is used instead of psi square, so that integration minus infinity to plus infinity n psi into n psi star dx dy dz is equal to 1, or n square integration minus infinity to plus infinity psi star dx dot dy dot dz is equal to 1, or integrate minus infinity to plus infinity psi star dx dy dz is equal to 1 upon n square, that is n power minus 2. Orthogonality. A particular wave function must be different from all other wave functions over the whole space. The chosen function should be independent of the other, that is, they should be orthogonal to each other. This is because if two particles had non-orthogonal wave function, then their description would not be unique, as one wave function could be described in terms of the other. Therefore, the wave function should be independent of one another. In other words, they should be orthogonal to one another. Mathematically, the conditions for orthogonality is that the product of the two wave functions when integrated over the whole space should be equal to 0. That is, if they are two wave functions psi 1 and psi 2, the complex conjugates psi 1 star and psi 2 star respectively, then for being orthogonal to one another, integration psi 1 psi 2 star dx dy dz is equal to 0 and integration psi 2 psi 1 star dx dy dz is equal to 0. If psi 1 and psi 2 are the real functions, integration psi 1 psi 2 dx dy dz is equal to 0, because psi 1 star is equal to psi 1 and psi 2 star is equal to psi 2. When they above the equation integration psi 1 psi 1 star dx dy dz is equal to 1 and integration psi 2 star dx dy dz is equal to 1, they are said to be normal wave functions. The wave functions which are both normalized and orthogonal are called the orthonormal functions. Next, heading 1.5, concept of atomic orbitals. Hinsburg principle, that is the uncertainty in the simultaneous measurements of position and momentum of the microscopic particles and the wave character of an electron, give a serious blow to Bohr's model. According to Bohr, electrons revolve in well-defined circular orbits, but the idea of uncertainty rejected the idea of the circular orbits and started the search for the theory and could explain stability of atom, dual character of matter, uncertainty principle. A new approach was established known as the wave mechanics. In 1927, Spondyger described the behavior of electron by a mathematical equation called the Spondyger wave equation described earlier. The most important outcome of the equation was the concept of orbital, in which the most probable reasons for the presence of electrons were described against the idea of circular path proposed by Bohr. Thus, an orbit can be defined as the the region in space around the nucleus where the probability of finding the electron is maximum. If a boundary is drawn which encloses the region where the probability of finding electron is high, the resultant picture gives the general outline of the orbital. For comparison purpose, the orbit and orbital are shown in the figure. The intensity of dots measures the relative probability of finding the electron. It may also be noted that the chances of finding the electron even exist outside the margin defined in an orbital. Let us summarize the difference between an orbit and an orbital. Difference between the orbit and orbital. Or first, orbit. An orbit is a well-defined circular path around the nucleus where the electron revolves. Orbital. An orbital represents the region where the probability of finding electron is maximum. Second, orbit. It represents planar motion of the electron. Orbital. The electron exhibits the three-dimensional motion. Third, orbit. All orbits are circular in shape. Orbital. The shapes of orbitals are different. Example, s orbital is spherical, while p orbital are dumbbell shaped and d orbitals are double dumbbell. Fourth, orbit. No directional character is shown by the orbital. Except s orbital, all remaining orbits are direction in nature. Fifth, orbit. An orbit can accommodate electrons equal to 2n square where n represents the principal quantum number. Orbital. An orbital can have a maximum of 2 electrons. Next heading 1.6 Quantum numbers. The hydrogen atom is the simplest example of one electron atom. Other examples of one electron ion is helium positive and lithium 2 positive, and ions in which all but one electron has been removed. In order to solve spondyger wave equation for hydrogen or hydrogen like ion with one electron, is set of 3 constants or numbers must be defined. The numbers or constants are called quantum numbers. These are designated as n, l and m. In addition to these 3 numbers, the fourth quantum number designated as s is also required to specify the spin of the electron around its own axis in addition to motion around the nucleus. A set of 4 quantum numbers which determine completely the position and energy of an electron in an atom are called quantum numbers. These are: first, principal quantum number n; second, azimuthal quantum number l; third, magnetic quantum number m; and fourth, spin quantum number s. First, principal quantum number n. It is the most important quantum number as it determines the principal energy level or shell to the which the electron belongs. It is denoted by the letter n and can have any integral value starting from 1 to infinity except 0, that is n is equal to 1, 2, 3, 4, infinity. The various principal energy levels or shells are also designated by the letters k, l, m and n, etc. starting from the nucleus. There is no limit to the number of cells or levels, but at present the 7th shell, n is equal to 7, is the highest shell occupied by the known 109 elements named so far. Principal quantum number n shell. First, second, third, fourth. Shell, first k, second l, third m and fourth n. The quantum number n determines the energy of the electron according to the formula En is equal to minus 2 pi square m e power 4 upon n square h square is equal to minus 2.178 into 10 raised to power minus 18 upon n square joule per atom is equal to minus 1.312 into 10 raised to power 6 upon n square joule per mole is equal to minus 1312 upon n square kilojoule per mole. The energy of the electron in K shell where n is equal to 1 is given by E1 is equal to minus 1312 upon 1 square is equal to minus 1312 kilojoule per mole. The energy of the electron in L shell where n is equal to 2 is given by E2 is equal to minus 1312 upon 2 square, that is minus 328 kilojoule per mole. It clearly proves that the lower the value of n, lower is the energy associated with it. Consequently, higher the value of n, higher the energy associated with it. The value of n is also measure of the average distance of the electron from the nucleus. In other words, the value of n determines the size of the electron cloud. Thus, in brief, as the value of n increases, the average distance of the electron cloud from the nucleus increase and also the energy of the electron in that shell increase. Second, azimuthal or angular quantum number L. Azimuthal or angular quantum number refers to the subshell or sublevel in a given principal energy shell to which the electron belongs. It is also named as secondary quantum number and is designated by the symbol L. This quantum number gives the energy of the electron due to the angular momentum of the electron. The magnitude of the angular momentum of the electron is related to L by the expression angular momentum is equal to root over L into L plus 1 dot h upon 2 pi, where L is equal to 0, 1, 2, 3 up to n minus 1. Each value of L represent a particular subshell or sublevel. Thus, if n is equal to 1, L can have only one value, that is 0. It means that there is only one type of subshell. In other words, for n is equal to 1, the subshell and shell are really identical. If n is equal to 2, L can have two values, 0 and 1. It means that an electron with n is equal to 2 has two subcells. If n is equal to 3, L can have three values, 0, 1 and 2. It means that an electron with n is equal to 3 has three subshells. If n is equal to 4, L can have four values, 0, 1, 2 and 3. It means that an electron with n is equal to 4 has four subcells. Thus, for each value of n, there are n different values of L. The different values of L are coded by the letters S, P, D, F. Depending upon the value of L, the designations S, P, D, F are the characteristics of the spectral lines found in the spectra. S, sharp, P, principal, D, diffused, and F, fundamental. Value of L, 0. Symbol S, designation sharp. Value of L, 1. Symbol P, designation principal. Value of L, 2. Symbol D, designation diffuse. Value of L, 3. Symbol F, designation fundamental. Thus it follows from the above discussion that the first principal shell K cell or n is equal to 1 has only one subshell L is equal to 0 called the S subshell. The second principal shell L cell or n is equal to 2 has two subshell, that is S subshell L is equal to 0 and P subshell L is equal to 1. The third principal shell M shell n is equal to 3 has three subshell, that is S subshell L is equal to 0, P subshell L is equal to 1 and D subshell L is equal to 2. Similarly, the fourth principal cell N is equal to 4 has four subshells, that is S subshell L is equal to 0, P subshell L is equal to 1 and D subshell L is equal to 2 and F subshell L is equal to 3. The designation of subshells and their numbers for the corresponding principal cell are summarized below. For 1, L is equal to 0, subshell designation 1s, number of subshell in a cell 1. For n is equal to 2, L 0 or 1, subshell designated 2s, 2 pi, number of subshell 2. For n is equal to 3, L 0, 1, 2, subshell 3s, 3p, 3d, number of subshell 3. For n is equal to 4, L 0, 1, 2, 3, subshell designation 4s, 4p, 4d, 4f, number of subshell in a shell is equal to 4. It is clear from the above tabulated values that the number of subshell in any principal cell is equal to the principal quantum number for all atoms with an exception of hydrogen. The energies of subshells within a given shell increases slightly with each other. L in the order S is less than P in the order F is the greater than D, then P, and then S. As an example, in the fourth shell n is equal to 4, the energies of the subshell increases as 4f is the highest, then 4d, then 4p, then 4s. For hydrogen atom, however, all the subshell have equal energies as 4s is equal to 4p is equal to 4d is equal to 4f. Third, magnetic quantum number m. This quantum number describes the preferred orientation of the electron in the presence of magnetic field. An electron is a charged particle and the momentum of the electron around the nucleus generates an electric field. This generated electric field in turn produces the magnetic field. Now when an external magnetic field is applied, there is an interaction between the magnetic field produced by the flow of the electron and the external magnetic field. This results in the electrons in a given subshell or orient themselves in some preferred region of space around the nucleus called the orbitals. Thus, the magnetic quantum number determines the number of preferred orientations of the electrons present in a subshell. Since each orientation corresponds to an orbital, therefore the magnetic quantum number determines the number of orbitals present in any subshell. The magnetic quantum number is designated by m. The value of m depends upon the values of L. For a given value of L, m can have integral values starting from minus L to 0 to plus L. Thus, for any value of L, m can have a total of 2 L plus 1 values. For example, if L is equal to 0, H subshell m can have only one value, that is m is equal to 0. It means that H subshell has only one orientation in space. In other words, H subshell has only one orbital called the s orbit. If L is equal to 1, P subshell m can have three values, that is m is equal to minus 1, 0, plus 1, which means P subshell has three distinct orientation in space. In other words, P subshell has three orbitals. Since these orbitals are oriented along x-axis, y-axis, and z-axis, these are designated as px, py, and pz. All the three orbitals where px, py, and pz have the same energy and are called degenerate, but this degeneracy is lifted up in the presence of magnetic field as shown in the figure. In case of L is equal to 2, m can have 5 values, that is m is equal to minus 2, minus 1, 0, plus 1, plus 2. It means the d subshell have 5 distinct orientation in space. In other words, d subshell have 5 d orbitals. These are designated as dxy, dyz, dzx, dx square minus y square, and dz square. Similarly, for L is equal to 3, f subshell m can have 7 values, that is m is equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. It means that f subshell has 7 distinct orientation in space. They are designated as fx cube, fy cube, fz cube, fxyz, fx into z square minus y square, fy into x square minus z square, and fz into y square minus x square. The relationship among the three quantum numbers n, l, and m and the orbitals is summarized in the table. Table 1.1, relationship between n, l, m and orbitals. Principal energy level 1, n1, l1, m0. Orbital subshell 1s, number of orbital per principal energy level 1. Principal energy level 2, n2, l0, 1 m 0 plus 1 0 minus 1. Orbital 2s 2p. Number of orbital 1 3 total 4. Third n 3 l 0 1 2 m 0. In case of 1 plus 1 0 minus 1. For 2 plus 2 plus 1 0 minus 1 minus 2. Orbital 3s 3p 3d. Number of orbital 1 3 5 total 9. Fourth n 4 l 0 1 2 3 m. For 0 0. For 1 plus 1 0 minus 1. For 2 plus 1 0 minus 1 minus 2. For 3 plus 2 plus 1 0 minus 1 minus 2 minus 3. Orbital 4s 4p 4d 4f. Number of orbital 1 3 5 7 total 16. Fourth, spin quantum number s. So far we have learned that the electron is continuously revolving around the nucleus. In addition, the electron is revolving more preciously, spinning around its own axis. The spinning of electron also produces a small magnetic field. The electrons can spin in the two ways, either clockwise or anti-clockwise. There is additional quantum number that describes the spin orientation of the electron and is called the spin quantum number. It is generally designated by s. For any particular value of magnetic quantum number, spin quantum number can have two values, that is either plus half or minus half. The positive or negative sign before half indicate the direction of spin, clockwise or anti-clockwise. Sometimes the spin values are represented by two arrows pointing in the opposite directions via above arrow or down arrow. The spinning electron behaves like a micromagnet, and the magnitude of angular momentum due to the spin is given by the expression angular momentum due to spinning of electron is equal to h upon 2 pi root s into s plus 1, where s represents the spin of the electron. It may be added that the spin quantum number s was not obtained from the solution of Schrödinger wave equation. This was introduced independently to account for the spin orientation of the electron around its own axis. Next, heading 1.7, wave functions of hydrogen atom. Schrödinger wave equation for the motion of a single particle of mass m expressed in terms of Cartesian coordinates x, y and z can be represented in the form del square psi plus 8 pi square m upon h square into e minus v into psi is equal to 0, or 1 upon m del square psi plus 8 pi square upon h square into e minus v into psi is equal to 0. The wave equation can be solved completely for the hydrogen atom that represents the simplest example of one electron atom, and other one electron system includes various ions: helium positive, lithium 2 positive, beryllium 3 positive, etc. In the hydrogen atom, there are two particles, namely the electron and the nucleus. The motion of both the particles can be expressed by the equation 1 upon me del square psi plus 1 upon mn del square psi plus 8 pi square h square into e minus v into psi is equal to 0, where me represents the mass of electron and mn represents the mass of hydrogen nucleus. The term e in the expression represents the total energy of the system. It is composed of two compounds, one corresponding to the translational motion of the atom, while the other corresponding to the energy of the electron with respect to the proton in the nucleus. Our basic aim is to calculate the energy of the electron with respect to the massive nucleus. This is possible only if we can eliminate the translational portion of the energy expressed in terms of Cartesian coordinates x, y and z from the wave equation. Schrödinger wave equation can also be conveniently expressed in terms of spherical polar coordinates expressed in terms of r, theta and psi, as the spherical polar coordinates expressed in terms of r, theta and psi are related to the Cartesian coordinates x, y and z as shown in the figure. The coordinates r, theta and psi locate the positions of a point A with respect to the starting point O, referred as the origin. Here r is the radial distance which measures distance of A from the origin O. Theta is the angle which the radial line OA makes with the z-axis, and psi is the angle which the projection of the radial line OA makes with the x-axis on xy plane. The Cartesian coordinates x, y, z and the polar coordinates r, theta, psi are related by the following simple geometrical relationship: x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta. Substituting the values of x, y and z in equation 1.15, get the equation 1.28. 1 upon r square dot curl upon curl r into r square dot curl psi upon curl r plus 1 upon r square sin theta dot curl upon curl theta into sin theta dot curl psi upon curl theta plus 1 upon r square sin square theta dot curl square psi upon curl psi square phi square plus 8 pi square mu upon h square into e minus v into psi is equal to 0, where mu is the reduced mass expressed as mu is equal to m1 m2 upon m1 plus m2, where m1 is the mass of the electron, m2 mass of the nucleus. The above equation now does not contain the variables x, y and z, and therefore does not involve translational motion of the atom. This second order partial differential equation, which relates the energy of the electron to the portion, can be easily solved by separating the three variables r, theta and phi. The solutions of the Schrödinger wave equation in terms of the spherical polar coordinates r, theta and psi can be expressed as the product of the three functions via r, small r, theta, small theta and psi, small psi, where psi, r, theta, psi is equal to r, theta, psi. where r is a function that depends upon the distance r only. Theta is a function that depends upon the angle theta only, and psi is a function depends upon the angle psi only. Phi only. The above expression can also be written as psi r theta phi is equal to r into theta dot phi is equal to r dot a, where r stands for the radial part that is dependent upon distance r alone, whereas a stands for angular part that is dependent upon the angle theta and phi. Substituting the value of 1.30 into the equation 1.28, introducing certain constants known as the quantum numbers, one gets a set of three. Substituting the value of 1.30 into the equation 1.28 and introducing Cartesian constants known as the quantum numbers, one gets a set of three independent differential equations containing only one of the three variables r, theta and psi. It is found that the wave function r depends upon the quantum number n and l, and the wave function theta depends upon the wave function l and m, whereas phi depends upon the quantum number m only. Taking into consideration all the quantum numbers, the expression 1.29 can be written as psi r theta phi is equal to r nl r theta lm and phi m is equal to r nl dot a lm and phi. It shows that wave function psi, or more preciously psi r theta phi, may be represented as the product of three functions. One of the functions r depends upon the distance r from the nucleus and is defined by two quantum numbers n and l. This function is called the radial wave function. Thus, the radial wave function gives the distribution of the electron as a function of distance r from the nucleus. The other functions a, theta and phi depends upon the direction angle theta and phi and is defined as the quantum numbers l and m. This function is called the angular wave function. Thus, the angular wave function determines the shape of the electron cloud or orbital. In summary, the complete wave function represents an orbital in which the radial part gives its size and the angular part determines its shapes. The molecular geometry could be better understood through the wave mechanical model of electron wave distribution around the nucleus. In the previous section, we have shown that the total wave function in the spherical polar coordinates r theta phi can be collectively expressed as psi r theta phi is equal to r nl is the radial part dot theta lm dot phi m is the angular part. The mathematical expression of the total wave function phi can be easily understood if we plot the radial r and the angular theta and phi parts of the wave function separately. Radial wave function. The radial part of the wave function r gives the distribution of the electron as a function of the distance r from the nucleus. It depends primarily on the values of quantum numbers n and l. The mathematical expressions of radial part of the wave function for 1s, 2s and 2p orbitals for the hydrogen and hydrogen-like atoms are given in table 1.2. Table 1.2 radial wave function psi for orbitals of hydrogen, quantum numbers n1, l0, orbitals 1s, radial part of wave function r is equal to z upon a naught whole power 3 upon 2 into e power minus z r upon a naught. Quantum number n is equal to 2, l is equal to 0. Orbitals 2s, radial part r is equal to z upon 2 a naught whole power 3 by 2 into 2 minus z r upon a naught into e power minus z r by 2 a naught. Next, n is equal to 2, l is equal to 1. Orbitals 2p, r is equal to 1 upon 2 root 6 into z upon a naught whole power 3 upon 2 into z r upon a naught into e power minus z r upon 2 a naught, where a naught is equal to h square upon 4 pi square m e square. For hydrogen atom, a naught is equal to 0.529 Armstrong and z is equal to 1. It is clear from the table 1.2 that the radial part wave function is governed mainly by the exponential terms e power minus z r upon n a naught, where e the base of natural logarithm, z is equal to atomic number for hydrogen, z is equal to 1, a naught is Bohr radius for hydrogen, a naught is equal to 0.529 Armstrong, n is equal to principal quantum number. The radial wave function can be represented by plotting r, which depends upon r part of wave function psi against distance r from the nucleus as shown in the figure. Features of radial wave function. First, an inspection of the radial part of the wave function for 1s orbital from table 1.2 indicates clearly that r depends mainly on the exponential term e power minus zr upon a0, as their other terms in the expression are constant. Z is equal to 1 for hydrogen atom and a0 is equal to 0.529 Armstrong. It shows that r for 1s should decrease with increase in r from the nucleus. This is reflected in the figure, where a continuous decrease in r is observed with increased distance r. Second, an inspection of table 1.2 reveals that the radial wave function for 2s orbital is governed mainly by the exponential term 2 minus zr upon a0 into e whole power minus zr upon 2 upon a0. Thus, the 2s orbital r should decrease with increase in r should become 0 at r is equal to 2a0 upon z as shown below. R is equal to 2 minus z upon a0 dot 2a0 upon z into E whole power minus Z upon A0 dot 2A0 upon Z is equal to 2 minus 2 into E power minus 1 is equal to 0. The point at which R is equal to 0 is called the node. Thus, that is the 2s orbital has a radial node which is spherical surface on which R is equal to 0. It surrounds the nucleus at a distance R is equal to 2A0 upon Z. Now as we move away, that is at R is less than 2A0, Z is equal to 1 for hydrogen atom, radial wave function becomes negative and decreases to a minimum value before increasing again to a infinite similarly small negative value. The net result is that 2s orbital has one node. Third, for 3s orbital R, the wave function becomes 0 at 2 points and shows a positive value beyond second node, acquiring a maximum value before decreasing to the infinitesimally small negative value. The 3s orbital thus has the two nodes. Fourth, an inspection of table 1.2 shows that the expression for the radial wave function for the 2p orbital of hydrogen atom Z is equal to 1 depends on the term R upon A0 into E power minus R upon 2A0. The expression becomes 0 only when R is equal to 0. Thus, the 2p orbital has no node as shown in the figure. The radial wave function increases to a maximum value and then decreases until it becomes infinitesimally small. The value is positive, although it is important to note that the radial wave function for all the three 2p orbitals, namely 2px, 2py and 2pz, is the same. Since the radial wave function gives the size of the orbital, it means that all three 2p orbitals will be of the same size. Fifth, the radial wave function R for 3p orbitals shows an increase in the beginning and it starts decreasing after attaining the maximum value. It is then followed by a negative value reaching to the minimum value before increasing to an infinitely small negative value. A radial node appears in the plot. This is shown in the figure. Sixth, the radial wave function specifies the size of the orbital, and the radial wave function for all the three 2p orbitals, that is 2px, 2py and 2pz, is the same. The three 2p orbitals thus are the same size. Seventh, the plots of R versus R for the 3d orbital and 4f orbital of hydrogen atom are similar to that of 2p orbital. Radial wave function plots show that the first orbital of each type, example 1s 2p orbital, has no nodes and have same positive sign everywhere. Similarly, the radial wave function R for 3d and 4f remain positive throughout and there are no nodes. These appears are maxima before decreasing the value of R to an infinitesimally small value as shown in the figure. Angular wave function. The angular wave function predicts the shape of the electron cloud and its orientation in the space. As mentioned earlier, the angular wave function depends on L and M value. The shape of the orbitals depends upon angle theta and phi, which determine the geometry. The angular part of the wave function varies depending upon the type of orbital involved, that is S, P, D and F. Thus, the probability of finding the electrons in any given direction from the nucleus without reference to its distance from the nucleus can be estimated. Mathematical expression for angular wave function for S, P and D orbitals are given in the figure table 1.3. Table 1.3, angular wave functions of the hydrogen atom. Quantum number L0, M0, orbital S, angular wave function 1 upon 4 pi whole power 1 by 2. L1, M0, orbital PZ, angular wave function 3 upon 4 pi whole power 1 by 2 cos theta. L1, M plus 1, orbital Px, angular wave function 3 upon 4 pi whole power 1 by 2 sin theta cos phi. L1, M minus 1, orbitals Py, angular wave function 3 upon 4 pi whole power 1 by 2 sin theta sin psi. L2, M0, orbital dz square, angular wave function 5 upon 16 pi whole power 1 by 2 3 cos square theta minus 1. The electron cloud may have spherical or non-spherical symmetry depending on the value of L. An s orbital L is equal to 0 has only one orientation and is spherically symmetrical. P orbital L is equal to 1 has 3 orientation. D orbital L is equal to 2 has 5 orientation depending upon the various values of M for the corresponding value of L. Features of angular wave function. First, for an s orbital, the angular wave function is independent of angle theta and phi and has a constant value. When a plot is drawn for this wave function in 3 dimensions, it is found to be spherical. Thus, an s orbital is spherically symmetrical in shape. Second, the wave function for the 3p orbitals and also for the d orbital depends upon the angle theta and phi, and therefore these orbitals are directional in nature and have different orientations around the nucleus. In summary, A. The radial wave function is maximum where R is equal to 0, that is the nucleus for all S subshell. B. The radial wave function is 0 when R is equal to 0 for all type of orbitals P, D and F except for S orbital. C. The point at which R changes sign or R is equal to 0 is called the nodal point. D. In general, a radial wave function has n minus L nodes. Example 2s, n is equal to 2, L is equal to 0 has 2 minus 0 minus 1 is equal to 1 node. 3s, n is equal to 3, L is equal to 0 has 3 minus 0 minus 1 is equal to 2 nodes. 2p, n is equal to 2, L is equal to 1 has 2 minus 1 minus 1 is equal to 0 node. 4p, n is equal to 4, L is equal to 1 has 4 minus 1 minus 1 is equal to 2 nodes. E. The first orbital of each type, example 1s, 2p, 3d and 4f has no nodes. F. The angular wave function depends on L and M value and is referred as the atomic orbital. G. The shapes of atomic orbitals depends upon the angles theta and phi and determine the geometry of the atom. Next heading 1.8 Probability distribution curves. The solution of spondyger wave equation gave a quantity psi whose square psi square can be used to outline the probability of finding an electron in a given region of space around the nucleus. The probability obtained from wave mechanics can be represented by three different ways. First, probability distribution curve. Radial wave function plot are as shown in figure indicate distribution of the electron with respect to its distance from the nucleus. There is another way to indicate such a distribution by studying the variation of psi with respect to r at fixed angles theta and phi for orbitals other than s. Because s orbitals are independent of angular dependence, the variation of psi square is nearly similar to the variation of psi except the psi square is either positive or 0. The plots of square of the wave function psi square, which describes the probability density of finding the electron at particular points as a function of r for 1s and 2s orbitals, are shown in figure. It can be seen that the probability of finding the electron is greatest at the nucleus. The probability, however, decreases as the distance from the nucleus increases. There is no point where the probability of finding electron becomes 0. Even at the points at large distance from the nucleus, there is some probability of finding the electron, although it is very small. This is in sharp contrast with Bohr's theory, according to which electron is at a fixed distance from the nucleus. Second, electron cloud representation. The probability distribution of electron can also be represented by means of electron density or the charge cloud. To understand this method, it is assumed that it is possible to take the photographs of the fast moving 1s electron in a hydrogen atom, and each snap gives the location of the movement. A series of snaps of these moving electrons are taken at very short intervals of time, and the developed film appear to be as shown in the figure. The cloud is denser in some region than the others. The probability of finding the electrons in a given region is proportional to the density of the charge cloud at that point. The probability is high in the region where cloud is dense. However, the cloud picture does not describe the path of the electron. It simply predicts where an electron is likely to be found. The electron cloud does not have a sharply defined boundary, since the probability of finding the electron at very large distance from the nucleus is very small but not zero. Shape of electron cloud gives the shape of the orbitals. Third, radial probability distribution curves for orbitals. A better picture to find the probability of the electron around the nucleus can be given by the radial probability distribution curves. Probability of finding an electron in a unit volume is given by quantity psi square, whereas the radial probability is given by the probability of finding an electron within a small radial space around the nucleus. In order to understand this concept, let us consider the space around the nucleus to be divided into a very large number of concentric cells. The volume of the spherical shell of extremely small thickness dr between the radius r and r plus dr will be given by 4 pi r square dr. Therefore, the total probability, known as the radial probability in any shell, is equal to the product of the volume of the shell 4 pi r square dr and the probability per unit volume in that shell. That is, radial probability is equal to volume of the shell into probability density is equal to 4 pi r square dr into psi square is equal to 4 pi r square psi square dr. The radial probability distribution depends upon the probability density psi square as well as on the volume of the shell. A plot of probability density for 1s orbital against the distance from the nucleus shows clearly that the probability is greatest near the nucleus, and it does not goes on decreasing with distance. For comparison, the volume of the shell is also plotted against distance from the nucleus in figure. With increased value of r from the distance, the volume of the shell goes on increasing. A careful examination of the plots in figure reveals that the probability density is the maximum close to the nucleus, whereas the radial probability corresponds to minimum near the nucleus. This is because of the volume of the shell near the nucleus, r is equal to 0, is extremely small. Practically, the value of the radial probability is 0 at the nucleus because the volume is 0. On moving away from the nucleus, the total probability of finding the electron in each shell goes on gradually increasing, reaches a maximum value for the shell at a certain distance from the nucleus, and then starts decreasing gradually as shown in figure. B. The maximum of the in the curves The small volume between the two spheres of radius r and r plus dr can be calculated as volume of shell is equal to volume of sphere with radius r plus dr minus volume of sphere with radius r. Volume of shell is equal to 4 pi upon 3 into r plus dr cube minus 4 pi upon 3 r cube is equal to 4 pi upon 3 into r cube plus 3r square dr plus 3r dr square minus 4 pi upon 3 r cube is equal to 4 pi upon 3 into r cube plus 3r square dr minus r cube. Dr is the small thickness and hence higher power of dr such as dr square and dr cube can be neglected is equal to 4 pi upon 3r square dr is equal to 4 pi r squared dot dr. Indicates the distance from the nucleus where the probability of finding the electron is maximum. The distance is called the distance of maximum probability r0. In case of hydrogen atom, the radius of maximum probability has been found to be 0.529 Armstrong. This value is in full agreement with the value calculated by Bohr for the radius of first orbit. Radial probability distribution curves for some of the orbitals of hydrogen atom are shown in figure. The radial probability plots for 2s orbital show two maxima and a minima in between. It means that there are two radii of maximum probability and one radius at which there is no chance of finding the electron. Thus, for 2s n is equal to 2, l is equal to 0 orbital, there are two regions of high probability and in between these two there is one node. Similarly, for 3s n is equal to 3, l is equal to 0 orbital, there are three regions of high probability and two nodes. Thus, in s orbital, number of high probability regions is equal to n, number of nodes is equal to n minus 1. N is inspection of the radial probability distribution curve for 2p and 3p orbitals reveals a rapid increase in the probability with the increase in distance r till a maxima is obtained. This is followed by the gradual decrease with the increase in the value of r. We find in the radial probability distribution curve for 3p orbital n is equal to 3, l is equal to 1. There are two maxima, high probability region and a node, zero probability region between them. Similarly, it has found in case of 4p orbital n is equal to 4, l is equal to 1. There are three regions of high probability and two nodes. Thus, we find in p orbital number of regions of high probability or maxima is equal to n minus 1, number of nodes is equal to n minus 2. The radial probability distribution curve in case of 3d n is equal to 3, l is equal to 2 orbital shows only one region of maximum probability. The radial probability distribution curve for 4d n is equal to 4, l is equal to 2 has two regions of maximum probability and one node as shown in figure. Similarly, there is only one high probability maxima in the radial probability distribution curve for 4f orbital as shown in figure. Let us summarize the results thus obtained. Orbitals 1s, 2p, 3d, 4f, first orbital of each type. Number of high probability region 1, number of nodes 0. 2s, 3p, 4d, 5f, second orbital of each type. Number of high probability region 2, number of nodes 1. Orbitals 3s, 4p, 5d, 6f, third orbital of each type. Number of high probability region 3, number of nodes 2. Next heading 1.9 shapes of orbitals. The actual wave function for the electron in a hydrogen atom is expressed as the product of radial part and the angular part. The angular part of the wave function depend upon the direction theta and phi, whereas the radial part depends upon the distance r from the nucleus. The part of the physical significance of the radial part has already been discussed in detail. Let us now discuss the angular part of the wave function which determines the shape of the orbital. If you recall, the radial part determines the size of the orbital. For s orbital, when l is equal to 0, the value of m is 0. That is, there is only one possible orientation. This means that the probability of finding an electron is the same in all directions at a given distance from the nucleus. It should therefore be spherical in shape because a sphere can be defined completely by a single value, that is its radius. Hence, s orbitals are non-directional and spherically symmetrical about the nucleus. The size of orbital depends upon the value of principal quantum number. The larger the value of n, the larger is the size of the orbital. Therefore, 2s orbital is larger than the 1s orbital. Both these orbitals are non-directional and spherical in shape. An important feature of 2s orbital is that there is a spherical shell within this orbital where the probability of finding the electron is 0. This is called the node or the nodal surface. The node corresponds to nearly zero value of probability in between the two maxima in the radial probability distribution curve. Thus, a 2s orbital differs from 1s orbital in being larger in size and having a nodal surface. Each s-type orbital has region of high probability represented by spherical shell equal to n. For example, 1s orbital has 1, 2s orbital has 2 and 3s orbital has 3 regions of high probability. Shape of p orbital. For p orbital, L is equal to 1, there are three values of m, namely -1, 0, +1. It means p subshell can have three possible orientations. These are represented by px, py, and pz. The distribution of electron density for an electron in the 2p orbital is not distributed in a symmetrical manner as in an s orbital. These three orbitals are equal in energy. Each p orbital consists of two lobes symmetrical about a particular axis depending upon the orientation of the lobes. These are denoted as 2px, 2py, and 2pz according as they are symmetrical about x, y, and z axis respectively. Two lobes of each orbital are separated by a nodal plane, a plane having the zero electron density. The p orbital thus is dumbbell shaped and has a directional character. The probability of finding the electron is equal in both the lobes. The p orbital of the higher energy level n is equal to 3, 4, 5, etc. have similar shape although their sizes are bigger. For example, the 3px orbital is shown in the figure. 3px orbital is larger in size than a 2px orbital and has two lobes on each side. The 3py and 3pz are also of this shape. Shape of d orbital. For d orbitals, the value of azimuthal number L is equal to 2. Thus, when L is equal to 2, there are 5 possible orientations corresponding to the allowed values of M. These are M is equal to -2, -1, 0, +1, and +2. Thus, there are 5 orbitals in each d subshell. For 3D subshell, these are designated as 3dxy, 3dyz, 3dzx. 3d x square minus y square and 3dz square. All these orbitals are degenerate, that is, they possess the same energy. However, these orbitals differ in orientation in space as shown in figure. The salient features of these orbitals are: first, the three orbitals, namely dxy, dyz, and dzx, consist of four lobes of high electron density in x, y, yz, and zx planes respectively. Each lobe bisects the principal axis into two equal halves. These are double dumbbell shape. Second, the 3d x square minus y square orbital has four lobes high electron density along the principal axis x and y. Third, the dz square orbital has a unique shape. It has two lobes along the z axis with a ring of electron density around the nucleus in the xy plane. In fact, dz square is formed by the linear combination of two orbitals 3dy square and minus z square and 3dz square minus x square, each of which has four lobes along the corresponding axis. Signs of wave function. No positive or negative sign was assigned to lobes while discussing the orbital shapes of s, p, and d orbitals in terms of probability distribution. The reason behind this was the probability distribution depends on psi square, which must always be positive. However, the angular part of the wave function may be positive or negative depending upon theta and phi. Angular part of the wave function for the hydrogen-like orbital are given in figure. The sign positive or negative in the lobes represent the sign of wave function in different directions. S orbital is always positive since it does not depend upon theta and phi, and there is no change in the shape, which depends spherical in all the cases. P orbital has two lobes, one positive and other negative. This can be explained by taking the example of 2pz orbital. The angular wave function of the orbital depend upon cos theta, which has positive signs between 0 to 90 degree and 270 to 360 degree, and negative signs between 90 to 270 degree along z-axis. Shapes and signs of py and px are similar in 2pz. The different values of cos theta for different angles from 0 to 180 degree are given below in table 1.4. The shapes of other orbitals can also be obtained by plotting the values of theta and phi. The graphs of 2p orbitals are given in figure. Like in 2pz orbital as shown above, one lobe in py and pz orbital has positive sign while the other lobe has a negative sign. Similarly, in case of d orbitals, there are four lobes. The opposite lobes of d orbitals have same signs. Thus, two of the lobes have positive sign and the other two lobes have negative sign. It is important to mention that when plot of probability density, that is psi square versus r, are drawn, the lobes do not have any signs. This is because psi square is always positive irrespective psi is positive or negative. Next, heading 1.10, energy level diagrams. Spondyger wave equation has successfully been solved exactly for hydrogen atom which has only one proton and one electron. Other common examples of hydrogen-like atoms are lithium, 2 positive, and helium, etc. However, difficulties arise in case of multi-electron systems. In such cases, approximate methods are used to find the solutions from which calculations of energy levels for orbitals are made. The energy values of various energy levels obtained from the solution of Spondyger wave equation have been found to be consistent with the experiment values obtained from the spectra of hydrogen or hydrogen-like atoms. The energy level diagram for the hydrogen is shown in figure. The energy values of various orbitals in a hydrogen atom depend only upon the principal quantum number n, are independent of the value of secondary quantum number L. Thus, all the subshell in the principal shell have same energy values. As an example, 2s and 2p subshell have same energies. Similarly, 3s, 3p and 3d subshell associated with the third shell n is equal to 3 have same energies. Similarly, in the fourth shell n is equal to 4, all the subshell via s, p, d and f have same energies. As already pointed out, in case of multi-electron system, the solutions of spondyger wave equation are not exact. In such cases, approximate methods are used which give nearly accurate solutions. The energy values of various energy levels are calculated. The energy level diagram for multi-electron system is shown in figure. Important features of energy level diagrams of multi-electron atoms are: first, in the hydrogen atom, the value of the principal quantum number n alone determines the energy of the orbitals. All the subshells of shell in case of hydrogen have the same energy. In case of multi-electron atom, the energies of various levels depends upon the principal quantum number n as well as on the angular quantum number L. Thus, all the subshells of a shell in case of multi-electron system have different energies. Second, in case of multi-electron atoms, for the same value of n, the higher the value of L, the higher is the energy. For example, 2p orbital n is equal to 2, L is equal to 1 has more energy than 2s orbital n is equal to 2, L is equal to 0. Similarly, the energies of subshells for n is equal to 3 are in the order 3s, n is equal to 3, L is equal to 0, less than 3p, n is equal to 3, L is equal to 1, less than 3d, n is equal to 3, L is equal to 2. Third, the difference in the energy of s and p orbital in the multi-electron system is small for the same value of n. The difference of energy amongst p and d orbitals is large. Fourth, in case of multi-electron system, the splitting of various subshells of a given shell is so large in some cases that orbitals belonging to lower energy level may possess more energies compared to orbitals of higher energy level. For example, energy of 3d orbital is more than that of 4s orbital. Similarly, 4d orbital is higher in energy than 5s orbital. The energy of an electron in an orbital depends upon first, nuclear charge, second, principal quantum number, and third, presence of electrons in the lower energy levels. In case of the multi-electron atoms, the electrons in the inner shell shield the outermost electrons from the nucleus. This effect is known as shielding effect or screening effect. The screening effect is different for different types of orbitals. As a result, s, p, d and f orbitals of even the same energy level experience different attractive forces of the nucleus. Therefore, these orbitals are held at different distances from the nucleus and have different energies. In case of hydrogen, there is only one electron present in the first energy level. Thus, there are no intervening electrons between the first energy level and the nucleus. Therefore, the electrons present in the first energy level does not experience any shielding effect. As a consequence, all different orbitals where s, p, d and f of the same energy level have same energy. The energy levels for multi-electron atoms differ from that of hydrogen atom in the following respects. Difference between energy level of hydrogen atom and multi-electron atom. First, hydrogen atom. The energy values of various levels in hydrogen atom depends solely on the value of principal quantum number. Multi-electron atom. The energy values of various level depends not only upon the principal quantum number but also on the angular quantum number. Second, hydrogen atom. All orbitals of a particular energy level have the same energy. Multi-electron atom. All orbitals of a particular energy level do not have the same energy. For example, the higher the value of L, the higher is the energy. Hydrogen atom, no shielding effect is involved. Multi-electron atom, there is a shielding effect of inner electrons that is exerted on the outer electrons. Next heading 1.11, Above principle. Above is a German word which means building up. Some people prefer to call the building up principle by its equivalent German name, the above principle. It is a procedure for filling up electrons in various orbitals. According to the principle, the electrons occupy the lowest energies orbitals available to them in the ground state of an atom. It means that the electrons enter the orbitals in the order of increasing energies. The lowest energy orbital available is being filled up first. In case of multi-electron atoms, the following sequence of filling the orbitals in the increasing order of energy is followed: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. The energy of an orbital is determined by the quantum number n and L. Therefore, the sequence of filling proceeds according to the following rules. First, orbitals are filled in order of increasing values of n plus L. Second, orbitals having the same value of n plus L, the orbital having lower value of n is filled up first. As an example, 3s orbital n plus L is equal to 3 plus 0 is equal to 3 is lower in energy than 3p orbital n plus L is equal to 3 plus 1 is equal to 4. Similarly, 2p orbital n plus L is equal to 2 plus 1 is equal to 3 and 3s orbital n plus L is equal to 3 plus 0 is equal to 3 have the same n plus L is equal to 3 value, but 2p orbital is associated with lower value of n is equal to 2 and therefore has lower energy than 3s orbital. This important n plus L rule is also known as Bohr-Bury's rule. It also helps to explain that certain orbitals with higher value of n but lower value of L possess less energy than orbital with lower value of n and higher value of L. For example, in case of 4s orbital, the n plus L value is 4 plus 0 is equal to 4, whereas in case of 3d orbital, the corresponding value is 3 plus 2 is equal to 5. It means 4s orbital has lesser energy than 3d orbital. Why is this energy of orbitals in different subshell of the same shell different in atoms with more than one electron? This is due to the screening of the inner electrons, which results in different effective nuclear charge on the outer electron occupying a particular subshell. The greater the effective nuclear charge, that is the charge actually felt by the outer electrons, greater will be the nuclear attraction for the electron and consequently lesser will be the energy of the subshell. We shall discuss later in detail while stating Slater's rule. N plus L values for various orbitals are summarized as n plus L orbitals: 1 1s, 2 2s, 3 2p and 3s, 4 3p and 4s, 5 3d 4p 5s, 6 4d 5p 6s, 7 4f 5d 6p 7s, 8 5f 6d 7p 8s. We have discussed that subshell in atoms are filled in order of increasing n plus L. When several subshells have the same values of n plus L, the subshell are filled in order of increasing n. This has been further simplified in the figure. To use, the diagram begins at 1s and follows the arrows of increasing n plus L. In describing the electronic configuration by s, p, d and f notations, one must remember that there is one orbital in an s subshell, 3 degenerate orbitals in a p subshell and 5 degenerate orbitals in d subshell and 7 degenerate orbitals in f subshell. Each orbital accommodate 2 electrons and a given subshell is filled before electrons are added to the next subshell. Each orbital can accommodate a maximum of 4l plus 2 electrons. As an example, n subshell L is equal to 0 has maximum of 2 electrons, p subshell L is equal to 1 is equal to 6 electrons, at d subshell L is equal to 2 10 electrons and f subshell L is equal to 3 14 electrons. Next heading 1.12 Pauli's exclusion principle. An important principle was proposed by Pauli 1925 which describes the number of electrons that an energy level can accommodate. According to the principle, no two electrons in an atom can have the same set of all four quantum numbers. It clearly means that for two electrons in the same orbital, three quantum number may be the same but the fourth must be different. Applications of this principle also helps in determining the maximum numbers of electrons that can be present in a given energy level. Electrons with the same set of the values of n, L and m belong to the same orbital. For example, consider the k shell where for each n is equal to L, can have only one value, L is equal to 0, m can also have one value, m is equal to 0. As a result, s can be either minus half or plus half. This means that although n, L and m are the same for the two electrons but their spin quantum numbers are different. On similar lines, for L shell for which n is equal to 2, L can have two values, L is equal to 0, L is equal to 1, whereas m can have one value for L is equal to 0, that is m is equal to 0, and three values for L is equal to 1, that is m is equal to minus 1, 0, plus 1. For each value of m, S can have two values, plus half and minus half. The 8 possible values of quantum number corresponding to L shell are as follows. It is evident that L shell can accommodate 8 electrons, 2 in the L is equal to 0 subshell and 6 in the L is equal to 1 subshell. Pauli's exclusion principle can also be stated as no more than 2 electrons may occupy any given orbital than 2 electrons do occupy one orbital. Their spins must be paired. First, an orbital cannot have more than 2 electrons. Second, if an orbital has 2 electrons, they must have an opposite spin. Now, there is a distribution table of electrons and their quantum numbers. A given principal energy level n can have maximum of n square orbitals and an orbital can have a maximum of 2 electrons. Thus, the maximum number of electrons in a principal energy level is restricted to 2n square. Therefore, keeping the Pauli's exclusion principle in view and the limitation of the permitted value of the quantum number, the number of electrons in an energy level can be calculated as given in the table 1.5. The Pauli exclusion principle expresses a fundamental property of electrons that cannot be explained in terms of classical mechanics. This property is of great importance in chemistry. It determines the electronic configuration of atoms and accounts for the importance of electron pair in the formation of covalent bonds. Another important rule that governs the filling of electrons in orbitals is called Hund's rule of maximum multiplicity. According to this rule, the electron try remain unpaired as far as possible. In other words, electron pairing will not take place in orbitals of the same energy, same subshell, until each orbital is singly filled with parallel spin. For example, each of the 3p orbitals of the 2p subshell gets one electron of parallel spin before any one of them occupies the second electron of opposite spin. This rule is especially useful in filling p, d and f subshell which have more than one kind of orbitals. Next heading 1.13, representation of electronic configuration. The way in which the electrons are arranged in atomic orbitals is called the electronic structure or in electronic configuration. The electronic configuration can be assigned by using three basic rules which have already been discussed. First, the building up above principle. Second, the Pauli's exclusion principle. Third, Hund's rule. Writing the electronic configuration involves first the main energy shell or level 1, 2, 3 is written first. Second, it is then followed by the subshell S, P, D or F. Third, the number of electrons in the particular subshell is shown in superscript to the subshell. For example, 3p power 4 indicates the location of 4 electrons in the p subshell of third energy level. Another method of representing the electronic configuration involves the use of an arrow for an electron, the direction of which gives the spin. The orbital is shown by the square of or a circle. If it is contains one electron that is half filled, a single arrow is put in the square or circle, whereas if it contains two electrons, that is the orbital is completely filled, two arrows pointing up and down are put in the square or in circle. The method is, however, used to explain certain characteristic features of the atom. A convenient method for writing the electronic configuration involves the usage of nearest noble gas. The atomic number of noble gas is followed by various orbitals. In fact, the configuration of the noble gas before the valence shell is simply represented by its symbol in square brackets. Example, in case of ring Z is equal to 30, the complete electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 and can be written Ar 3d10, 4s2 because the noble gas of argon takes care of 18 electrons. Electronic configuration of elements. The distribution of electrons into different shells, subshells or orbitals of an atom is called its electronic configuration. Keeping in view the above mentioned rules are and representing the orbital by a box and an electron with its direction of spin by an arrow, the electronic configuration of an atom of any element can be assigned. Starting with hydrogen and progressing in order of increasing atomic number, each successive element contains one more electron than its preceding elements, and this continue with exception throughout the periodic table. The electronic configuration of first few elements are discussed as hydrogen, Z is equal to 1. The ground state electronic configuration of hydrogen atom is obtained by placing the electron in the lowest energy subshell, that is 1s. Thus, the electronic configuration is 1s1. Helium Z is equal to 2. Both the electrons can be filled into 1s orbital, but they should have opposite spin in accordance with Pauli exclusion principle, that is 1s2. Lithium Z is equal to 3. The two electrons filled the 1s orbital, while the remaining one electron fills the orbital of the next higher energy, that is 2s. Thus, the electronic configuration becomes 1s2, 2s1. Beryllium Z is equal to 4. It has 4 electrons, 2 electrons filled with 1s orbital, and the remaining occupy the 2s orbitals. Thus, the electronic configuration of beryllium is 1s2, 2s2. Boron Z is equal to 5. 2 electrons occupy 1s orbital, and the next 2 can occupy 2s orbitals. The fifth electron can occupy any one of the 3 2p orbitals, that is 2px, 2py or 2pz, because all are the same energy. The configuration can be represented as 1s2, 2s2, 2px1 or 1s2, 2s2, 2py or 1s2, 2s2, 2pz. Carbon Z is equal to 6 and nitrogen Z is equal to 7. For carbon Z is equal to 6, we have two possibilities. The second electron in the p orbital can either pair up with the first one in the same p orbital and can have the opposite spin, or can enter into a different p orbitals and have the same spin. Thus, the acceptable electronic configuration for carbon Z is equal to 6 is as follows: 1s2, 2s2, 2px, 2py, or in the case of nitrogen, Z is equal to 7 in accordance with Hund's rule. Each of the 3 2p orbitals are singly occupied with electrons having the parallel spin, that is 1s2, 2s2, 2px, 2py, 2z. Or oxygen, Z is equal to 8. fluorine Z is equal to 9 and neon Z is equal to 10. The pairing of electrons starts with oxygen and ends at neon. Oxygen Z is equal to 8, 1s2 2s2 2p4. Fluorine Z is equal to 9, 1s2 2s2 2p5. Neon Z is equal to 10, 1s2 2s2 2p6. From sodium Z is equal to 11 to argon Z is equal to 18. The electronic configuration of these elements are similarly written. In these elements 3s and 3p orbitals are successfully filled with one electron, one at a time, following the general principle. For the sake of simplicity, the detailed electronic configuration of the noble gas core preceding the valence electrons can be represented by the symbol of the noble gas in the square brackets. Sodium Z is equal to 11, 1s2 2s2 2p6 3s1. Magnesium Z is equal to 12, 1s2 2s2 2p6 3s2. Aluminium Z is equal to 13, 1s2 2s2 2p6 3s2 3px. Silicon Z is equal to 14, 1s2 2s2 2p6 3s2 3px 3py. Phosphorus Z is equal to 15, 1s2 2s2 2p6 3s2 3px 3py 3pz. Sulfur Z is equal to 16, 1s2 2s2 2p6 3s2 3px2 3py2 3pz. Chlorine Z is equal to 17, 1s2 2s2 2p6 3s2 3px2 3py2 3pz. Argon Z is equal to 18, 1s2 2s2 2p6 3s2 3px2 3py2 3pz2. Potassium Z is equal to 19 and calcium Z is equal to 20. With potassium, the filling of 4s orbitals begins since the energy of 4s orbital is slightly lower than that of 3d orbital. Potassium Z is equal to 19, 1s2 2s2 2p6 3s2 3p6 4s1. Calcium Z is equal to 20, 1s2 2s2 2p6 3s2 3p6 4s2. Here, argon represents the noble gas with 1s2 2s2 2p6 3s2 3p6 electronic configuration. Electronic configuration and filling of orbitals from atomic number Z is equal to 21 and to Z is equal to 30 is given in the table 1.6. Electronic configuration of elements with atomic number beyond 10.3. All the elements after atomic number 103 are filled in the 6d orbitals. The electronic configuration of the elements with atomic number 103 in 5f14 6d1 7s2. As more and more elements will be discovered, they are anticipated to occupy 6d orbitals till the 6d transition series is complete. Because these elements have short lifespan, there are conflicting elements of their discovered. In order to diffuse the controversy, IUPAC recommend a novel way of naming these elements after atomic number 101. The naming is done by combining the following roots of the 3 digits and then adding em at the end: 0 nil, 1 un, 2 bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 hept, 8 oct, 9 un. Thus, for example, an element with atomic number 108 will be named according to IUPAC as un plus nil plus oct plus em is equal to unleoctium. However, recently the element up to 109 have been named after the names of some of the reputed scientists. Electronic configuration of ions. During the formation of ions, electrons are either lost or gained. The loss of electrons result in the formation of cation, while gain of electrons lead to the formation of an ion. The number of electrons added or removed both from the valence shell is equal to the numerical value of charge present on the ion. Following the general concept and rules for filling the orbitals, one can easily write the electronic configuration of ions as follows. Anions F is equal to F. Anions F Z is equal to 9, 1s2 2s2 2p5. F minus Z is equal to 9, 1s2 2s2 2p6. N Z is equal to 7, 1s2 2s2 2p3. N 3 negative Z is equal to 7, 1s2 2s2 2p6. S Z is equal to 16, 1s2 2s2 2p6 3s2 3px square 3p1 3p1. S 2 negative Z is equal to 16, 1s2 2s2 2p6 3s2 3px2 3py2 3pz2. Cations. Sodium Z is equal to 11, 1s2 2s2 2p6 3s1. Na positive Z is equal to 11, 1s2 2s2 2p6. Magnesium Mg Z is equal to 12, 1s2 2s2 2p6 3s2. Mg 2 positive Z is equal to 12, 1s2 2s2 2p6. Aluminium Z is equal to 13, 1s2 2s2 2p6 3s2 3p1. Aluminium 3 positive Z is equal to 13, 1s2 2s2 2p6. It is important to note that in case of transition elements, electrons with the higher value of N are removed first. For example, in case of copper, it is the 4s electrons that are removed first, then the 3d electrons. For example, the electronic configuration of copper Z is equal to 29 is Cu Z is equal to 29, 1s2 2s2 2p6 3s2 3p6 3d 10 4s1. When Cu2 positive is formed, Cu2 positive Z is equal to 29, 1s2 2s2 2p6 3s2 3p6 3d9. Similarly, in case of other cations, Fe Z is equal to 26, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Fe2 positive Z is equal to 26, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Fe3 positive Z is equal to 26, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. COZ is equal to 27, 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. CO2 positive Z is equal to 27, 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. CO3 positive Z is equal to 27, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. It is worthwhile to note here that while writing the electronic configuration of cations, the electronic configuration of the atoms should be written first, and when the electrons equal to the units of positive charge should be removed starting from the outermost shell. Limitations of above principle. Above principle is quite useful to formulate the ground state electronic configuration of atoms, although electronic configuration based upon above order of filling agree mostly with those derived experimentally by various spectroscopic studies, yet there are quite a few exception. These happens mostly in the cases where the subshell involved in configuration are exceedingly closely spaced and are likely to exchange positions. Some of above limitations are listed below. First, electronic configuration of atoms on ionization. The above principle cannot be used to predict electronic configuration of atoms on ionization. It fails to tell which electrons are to be removed when an ion is formed from an atom. For example, according to above principle, the electronic configuration of iron Z is equal to 26 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. While building the configuration of an atom of iron, the last electron adds onto the 3d orbital. Fe plus 2 ion is formed by the loss of 2 electrons, and it has been found experimentally by spectral studies that Fe plus 2 has the configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And note the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. It means that during the ionization, 4s electrons are lost in preference to 3d electrons, even though the 3d electrons are lost to be added during the building up of configuration. It clearly means that after filling the electrons in the Fe atom, the 3d subshell has the lower energy than 4s subshell, which goes against the above principle. In other transition and the inner transition elements, the electron are removed first from ns orbital in preference to n-1 d or n-2 f subshell. Through n-1 d or n-2 f subshell are filled later. Second, exceptional configuration of atoms involving their ns and n-1 d subshells. Filling of electrons should take place first in ns orbital followed by n-1 d orbitals. But the configuration of chromium Z is equal to 24 and copper Z is equal to 29 are exceptional, as these do not follow the above principle. The electronic configuration expected for chromium and copper are Cr is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. Cu is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. However, the actual electronic configuration exhibited by these elements is Cr is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Cu is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d 10, 4s1. This is attributed to the fact that half-filled and completely filled subshell, that is D5, D10, have lower energy and hence possess extra stability. Thus, in order to acquire the increased stability, one of the 4s electron goes to nearby 3d orbital, so that 3d subshell become half-filled in case of chromium and completely filled in case of copper. Following on similar lines, the experimentally observed configuration of silver Z is equal to 47, molybdenum Z is equal to 42, gadolinium Z is equal to 64, and gold Z is equal to 79, and some other elements are different as expected from above configuration. Similarly, the extra stability of filled D10 configuration is seen in case of palladium Z is equal to 46, where 2 electrons are shifted to give the configuration for D10 5s0 instead of 4d8 5s2 as given by above. Third, electronic configuration of lanthanoids. Above principle could not explain the electronic configuration of lanthanoids Z is equal to 57 to 71. In fact, the sequence of filling various orbitals in case of lanthanoids deviates slightly from the prescribed arrangement shown in figure. After the filling 6s orbitals in case of barium Z is equal to 57, the next electron of lanthanoids Z is equal to 57 should fall in the 4f subshell. In fact, this does not happen. Rather than next electron enters the 5d subshell, the electronic configuration thus becomes La is equal to x xenon into 6s2 5d1. However, after lanthanoid Z is equal to 57, the filling of electrons in the next elements were 58 to 71, cerium to lutetium, occurs in the 4f shell, and even the previous electron in 5d orbital in lanthanum is also shifted to 4f subshell. The filling of 4d restarts only after the 4f subshell is completely filled with LA z is equal to 71. Fourth, electronic configuration of actinoids. The electronic configuration of actinoids z is equal to 89 to 103 can also not be predicted correctly by above principle. The sequence of filling again deviate from the normal assigned trend immediately after filling the 7s subshell. In case of radium, z is equal to 88. The next electron in actinium, z is equal to 89, should enter the 5f subshell. However, the electron enters the 6d subshell. The electronic configuration thus becomes AC is equal to Rn 7s to 6d1. The reason for such exceptional configuration is attributed to small energy difference between the 4f and 5d subshell, where the electron transfer occurs easily. Fifth, anomalous configuration of some atoms of second and third transition series. The electronic configuration of some atoms of second and third transition series displays irregularities as shown below. Zirconium Z is equal to 40 possess the electronic configuration Kr4d25s2. The next element, niobium Nb Z is equal to 41, is expected to have electronic configuration 4d35s2 according to above principle. However, the experimentally determined configuration is 4d45s1. Similarly, there are good number of atoms which do not obey above principle and are listed below. Nb Z is equal to 41, Ru Z is equal to NB Z is equal to 41 4d4 5s1, Ru Z is equal to 44 4d7 5s1, RH Z is equal to 45 4s8 5s1, PD Z is equal to 46 4d10 5s0. It is very difficult to pinpoint the cause of this anomalous behavior. In fact, the anomalous behavior may be due to several factors such as electron nucleus attraction, electron repulsion, shielding of electrons, exchange and binding energies. Cause of stability of half-filled and completely filled orbitals. The electronic configuration of most of the atoms generally follow the generalized rules. However, in certain elements, when two subshells differ slightly in their energies, an electron may shift from a subshell of lower energy to a subshell of higher energy only if such a shift results in the symmetrical distribution, that is either completely filled or exactly half filled, of the electrons in the various orbitals of the subshell of higher energy. This is due to the following two reasons. A. Symmetrical distribution. The concept symmetry leads to stability implies that the electronic configuration in which all the orbitals of the same subshell are either completely filled or are exactly half filled are most stable because of symmetrical distribution of electrons. B. Exchange energy. The stability of the half-filled and completely filled d orbitals can also be explained in terms of lowering of energy due to exchange energy for a set of two electrons of parallel spins. The exchange energies depends upon the possible exchangeable coordinates between sets of two electrons of parallel spin. It is well known that two electrons with parallel spin remain maximum away from each other as compared to two electrons with opposite spin. Consequently, the repulsion is less in the former case and more in later case. The lowering of energy depends upon the number of possible exchangeable coordinates between sets of two electrons of parallel spins. The larger the number of sets, the greater is the exchange energy. For example, in a system containing the electronic arrangement 3d5 4s1, there are 6 unpaired electrons for parallel spin. The number of possible exchange sets can be calculated as follows. The first electron can exchange coordinates with any of the 5 remaining electrons, that is 2, 3, 4, 5, 6. So number of possible sets with parallel spin is equal to 5. Similarly, second 2 electrons can exchange coordinates with one of the 4 electrons we have with 3, 4, 5 and 6. So number of possible exchange sets with parallel spin is equal to 4. Following the same trend, the number of possible exchange sets for third, 3, 4th, 4 and 5th 5 electrons with parallel spin are 3, 2 and 1 respectively. Thus, in case of the 3d5 4s1 arrangement, the total number of possible sets of electrons with parallel spin 5 plus 4 plus 3 plus 2 plus 1 is equal to 15. Let us now consider the case of electronic configuration 3d4 4s2. There are only 5 electrons with the parallel spin, that is 1, 2, 3, 4 and 5, while 6 with the opposite spin. The number of possible exchange sets with parallel spin counted here for 1, 2, 3, 4 and 5 electrons are 4, 3, 2 and 1 respectively. Thus, the total number of sets electrons with parallel spin is equal to 4 plus 3 plus 2 plus 1 is equal to 10. It clearly shows that while in case of 3d10 4s1 lowering of energy is due to 15 possible sets, whereas in case of 3d9 4s2 arrangement the lowering of energy is due to 10 possible sets. Thus, the lowering in case of 3d10-4s1 is more than the 3d9-4s2 system, and hence 3d10-4s1 arrangement is more stable. Next, heading 1.14, the shielding effect and the effective nuclear charge. Most of the physical and chemical properties of the elements can be explained on the basis of electronic configuration of elements. As the electronic configuration helps in explaining many properties, same way the role of nuclear charge is accounted for the explanation of periodicity of many properties. As an example, consider the behavior of ionization energies in the periodic table. It is known that the magnitude of ionization potential depends upon the following factors. First, size of the atom. Second, the nuclear charge. Third, the screening effect of the inner shells. Fourth, the extent to which the outermost electron penetrates into the charge cloud set up by the inner lying electrons. The larger the size of an atom, the less tightly are the valence electrons held by the positive charge on the nucleus, and the lower is the value of the ionization energy. The greater the charge on the nucleus, more difficult it is to remove an electron from the atom, and hence greater is the ionization energy. The existence of the inner shell of electron between the valence shell and the nucleus to a certain extent shield the outermost electron from the nucleus because of attractive force of the nucleus on the electrons is partially counterbalanced by the repulsive force from the inner shell of electrons. Thus, an increase in the number of electrons in the inner shell tends to decrease the ionization energy. Thus, the reduction of the nuclear charge or pull on the outermost electrons of an atom by the intervening electrons is called the screening or the shielding effect. The greater the number of electrons in the inner shell, greater is the shielding effect. The magnitude of the screening effect does not depend only on the number of electrons on the inner shell, but mainly upon the type of orbital occupied by the electrons. The degree of penetration of the electrons in a given principal quantum number level decreases in the order. Greatest is S, then P, then D, and then F. The difference in the penetration is due to different shapes due to greater penetration effect, and S electron screens the nucleus more effectively than the P electrons, and so on. Now it has become obvious that the nuclear charge as given by the number of protons Z is not the actual nuclear charge or the force experienced by the outermost shell electrons, but is much less than its is called effective nuclear charge Z star. So Z star is equal to Z minus rho. Here rho is the screening or shielding constant. According to Bohr, the allowed values of sigma is the screening or shielding constant. According to Bohr, the allowed values of screening energy for an electron in hydrogen atom is given by En is equal to minus me power 4 z square upon 8 r0 n square h square. It is obvious that the energy of the outermost electron, which is held loosely, will change rapidly when the principal quantum number n changes. In the hydrogen atom, the energy of the electron is 1312.1 kilojoule per mole. It means that 1312.1 kilojoule per mole of the energy must be supplied to remove this electron. It is in fact is the ionization energy of the hydrogen atom EH. The ionization energies of some other elements can be calculated using the above equation. For example, for helium atom, E helium is equal to 4 into EH as ZH is equal to 1 and ZHE is equal to 2, so that Z square is equal to 4. E helium is equal to 4 into 1312.1 is equal to 5248.4 kilojoule per mole. But the observed value of ionization energy for helium is 2372 kilojoule per mole, which is far less than the expected value. Now, if this value of 2372 kilojoule per mole is put in equation 1.31 for the calculation of Z, it comes out to be 1.35 for helium. Hence, the charge of the nucleus as felt by the electrons of helium gets reduced from 2 to 1.35. When calculations are made on the same line for lithium, it is found that charge of nucleus has felt by outer electrons get reduced from 3 to 1.59, and for beryllium it is reduced from 4 to 1.7 units. It is now obvious that every element some factor sigma must be subtracted from the nuclear charge Z to get the actual charge felt by outermost electron. This is called the effective nuclear charge Z star, and the factor is called shielding or screening constant, so that Z star is equal to Z minus sigma. Slater's rule. In 1930, J.C. Slater proposed a set of empirical rules to understand the concept of effective nuclear charge. He proposed a formula that related Z effective to the actual nuclear charge Z. Z effective is equal to Z minus S, where S is called Slater's screening constant. Slater derived a series of empirical rules for calculating the value of S. It is possible to evaluate the shielding or screening constant, which is defined as a measure of the extent to which the intervening electrons shield the outer electrons from the nuclear charge. From the knowledge of screening constant, the effective nuclear charge is calculated by subtracting it from the nuclear charge. The Slater's rule for calculating shielding constant SR. First, the electronic configuration of element is first written in the following order and groupings: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and so on. Second, electron in any group higher in sequence than the electron under consideration contributes 0 to the screening constant. Third, electron in the same group contributes 0.35 per electron except in the 1s group where it contributes 0.30 instead of 0.35. Fourth, for an electron in the ns or np orbital, all electrons in the n-1 shell contribute 0.85 per electron, and all electrons in the next inner shell, that is n-2 and lower shells, contribute s is equal to 1.00 each. Fifth, for an electron in nd or nf orbital, all electrons in the lower groups contribute s is equal to 1.0. Calculation of shielding or screening effect. First, the electronic configuration is written as 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 4s, 5p, and so on. Second, the shielding constant for an electron considered in the groups of sp electrons is the sum of following contributions: A. 0 for electrons in groups outside the one considered. B. 0.35 for each other electron in the group under consideration. In case of 1s electron, it is 0.30 instead of 0.35. C. 0.85 for each electron in the next inner shell, that is n-1. D. 1.00 for each electron in all other inner shells other than n-1, that is n-2, n-3, etc. Then here are some examples based upon Slater's rule. Applications of Slater's rule. The concept of effective nuclear charge is quite useful and important in many respects. Some of its applications are the following. First, it helps justifying the filling of 4s orbital, ns orbital, first then 3d orbital, n-1d orbital. Let us take the case when the last electron is added to 4s orbital. Then the electronic configuration of potassium case, Z is equal to 19, can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. In such case, the grouping of orbital can be done like 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The screening constant can be calculated as number of electrons in 3s and 3p into 0.85 plus number of electrons in 2s, 2p and 1s group into 1.00 is equal to 8 into 0.85 plus 10 into 1.00 is equal to 6.8 plus 10 is equal to 16.80. Effective nuclear charge Z star is equal to Z minus sigma is equal to 19 minus 16.80, which is equal to 2.20. Now, if the last electron enters the d subshell, then the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. The group is done like 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. The screening constant is calculated as number of electrons in 3s, 3p, 2s, 2p, 1s group into 1.00 is equal to 18 into 1.00, that is 18.00. Effective nuclear charge 19 minus 18, that is 1. Comparing the effective nuclear charges, it can be concluded that 3d electrons faces lesser effective nuclear charge than the 4s electron in potassium atom. It means that when the last electron is present in the 3d orbital, it is less tightly bound to the nucleus than when it is present in the 4s orbital. As a consequence, the additional electron in potassium atom enters 4s orbital in preference to 3d orbital. Second, It explains why 4s electrons are lost prior to 3d electrons while formation of cations in transition elements. Consider the case of vanadium. The electronic configuration of Vz is equal to 23 is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. The electronic configuration of the ion when 2 electrons are lost is V plus 2. 1s2, 2s2, 2p6, 3s2, 3p6, 3d3 and not 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. This can again be explained on the basis of the effective nuclear charge for the 4s and 3d electrons. For 4s electrons, the orbitals are grouped like 1s2 ratio 2s2 2p6 ratio 3s2 3p6 ratio 3d3 ratio 4s2. The screening constant may be calculated as number of electrons in 4s group minus 1 into 0.35 plus number of electrons in n minus 1th group into 0.85 plus number of electrons in n minus 2 n minus 3 group into 1 is equal to 1 into 0.35 plus 11 into 0.85 plus 10 into 1 is equal to 19.70. Effective nuclear charge Z star minus Z star is equal to Z minus sigma is equal to 23 minus 19.70 is equal to 3.30. In the case of the 3d electrons, the grouping is done like 1s2 ratio 2s2 2p6 ratio 3s2 3p6 ratio 3d3. The screening constant is calculated as number of electrons in 3d group minus 1 into 0.35 plus number of electrons in the inner groups into 1 is equal to 2 into 0.35 plus 18 into 1 is equal to 18.70. Effective nuclear charge Z star is equal to 23 minus 18.70 is equal to 4.30. It is clear that 3d electrons have greater pull towards the nucleus compared to 4s electrons and thus are held tightly to the nucleus. Therefore, the 4s electrons are removed in preference to 3d. Similar behavior is observed in case of other transition metals. Third, it explains why a cation is always smaller than the parent atom. It can be explained on the basis of the effective nuclear charge. Let us take the example of lithium and lithium star ion. In case of lithium, the screening constant may be calculated as follows. The grouping lithium can be done as 3 Li 1 is 2 ratio 2s1. Screening constant is equal to 2 into 0.85 is equal to 1.70. Effective nuclear charge Z minus sigma is equal to 3 minus 1.70 is equal to 1.30. In case of lithium star, the grouping is 3 Li star 1 is 2. Screening constant is equal to 1 into 0.30 is equal to 0.30. Effective nuclear charge is equal to Z minus sigma is equal to 3 minus 0.30 is equal to 2.70. The effective nuclear charge of lithium positive is more than lithium and thus the size is smaller Li 1 to 3 picometer, Li positive 60 picometer. Fourth, it explains why an ion is always larger than the parent atom. Now moving on the similar lines, take the example of chlorine and chlorine negative and compare the two in terms of the effective nuclear charge. In case of chlorine, the grouping can be done like chlorine 1s2, 2s2, 2p6, 3s2, 3p5. Screening constant 6 into 0.35 plus 8 into 0.85 plus 1.0 into 2 is equal to 10.90. Effective nuclear charge Z minus sigma is equal to 17 minus 10.90 is equal to 6.1. In case of chlorine negative ion, the electronic configuration grouping can be done like chlorine negative 1s2, 2s2, 2p6, 3s2, 3p6. Screening constant 7 into 0.35 plus 8 into 0.85 plus 1 into 2 is equal to 11.25. Effective nuclear charge 17 minus 11.25 is equal to 5.75. It is obvious that the effective nuclear charge in case of chlorine is greater than that of chlorine negative. Thus, the size of chlorine negative should be larger than chlorine atom. Chlorine is equal to 72 picometer. Chlorine negative is equal to 136 picometer. Sixth, it also explains the anomalous configuration of some elements. Limitations of Slater's rule. Slater's rule are very useful for calculating the effective nuclear charge for atoms and ions. However, it has several limitations which are detailed below. First, both s and p orbitals are grouped together for evaluating the effective nuclear charge. This is a faulty assumption because the radial probability distribution curves for a given n indicate a higher penetration or shielding effect over s as compared to p. Second, according to Slater's rules, all the electrons irrespective of s, p, d and f orbital present in the shells lower than n-1 shell shield the n shell electron with equal contribution of 1.00. This is not justified because energetically different orbitals cannot contribute equally. Third, Slater's rule are less reliable, especially in case of heavier elements. So this was all about atomic structure.